So when we talk about conservation of energy, we're talking about the total energy at some initial point and a final point being the same value. However, the form that that energy has can change. So remember, mechanical energy consists of two things, kinetic and potential energy. So you can have varying amounts of the kinetic and potential energy at the initial and the final stages. So the split can be different provided the total sum is the same. So if the total sum is say 100, in one place you could have 80-20, in the other you could have 50-50 or 100-0, 60-40, whatever, anything that adds up to 100. Yeah. So how does energy get transferred? Okay. Energy could be transferred in several ways. One is by doing work. We saw that work is intimately related to energy. It's the force times the displacement in the direction of the force, okay? Or the dot product between the force and the displacement. Energy is also transferred by way of heat. The exchange of energy is called heat, okay? And this could happen through radiation, convection, and convection currents in the fluid. You can have actual waves, mechanical waves, which we will come to in chapters 13 and 14. So any kind of wave motion carries energy with it, okay, whether it's a sound wave, a water wave, or seismic wave, which are earthquake waves. Yeah. Electrical transmission carries energy with it. You know, when you switch your light on, the energy is coming via the electrical current. So that's another way of transferring energy. And electromagnetic radiation, after all the energy that we receive on the earth is from the sun, which is electromagnetic radiation. Okay, and you'll learn about that more in physics too. In general, we cannot create or destroy energy. There's a fixed amount of energy. We can change, it can change forms, but it can never be created or destroyed. So if the total energy of a system does not remain constant, then that energy must have crossed a boundary and the system is not isolated anymore. Yeah? Next we come to power. Okay, this is the last concept that we need to study in this chapter. And power is the rate of energy transfer. Okay, so energy or work, how fast it is done. So work divided by time, or energy divided by time, is going to give you power. This sign means this is the average power. Remember, work can be written as force times displacement. And displacement divided by time gives you velocity, average velocity. So this can also be written as force times average velocity. Units for power are watts. This W is different from this W. Okay, this is the unit for power, watts. This is work. So 1 watt equals 1 joule per second. So if 1 joule per second is transferred, then we get 1 watt of energy, okay? Or 1 watt of power, sorry. Typically, if you look at your electricity bill, it will be using something called horsepowers, and 1 horsepower is got a conversion to 746 watts of energy, okay? So typically, you might see on electricity bills kilowatt hours, okay? And that's a unit of work or energy in terms of power, okay? So kilowatt hour, since it's multiplying time with the kilowatts, it's going to be a unit for energy and not of power. But you might see your electric bill in terms of kilowatt hours. Okay. So just to give you a flavor of how much energy is consumed per unit time when we are doing various activities, when you're sleeping, you're consuming 83 units or 83 watts, okay? Over the same amount of time, if you are cycling, you're consuming 700 watts. And if you're sprinting, that's running quite fast, is 2,415, okay? So let's look at some simple problems here. What is the cost of running a 0.2 kilowatt computer 6 hours per day for 30 days if the cost of electricity is 12 cents per kilowatt hour. Okay. So when you have this kind of question, you see that there are several different units. There's kilowatts here, and luckily the rate is given per kilowatt hour, right? So you want everything, you want to know how many hours you're going to run this, yeah, so that you can apply this rate. I would convert all these things into the units for the rate given here, since you're going to have to finally get the cost in terms of multiplying by this unit here. So how many kilowatt hours are we using? We're using 0.2 kilowatts for 6 hours each day for 30 days. So we need to multiply it by 30. And then that gives us kilowatt hours, which is 36 kilowatt hours. Then we can go ahead and multiply that by the rate. And now notice how these units are the same, kilowatt hours. And that gives us $4.32. That's what it's going to cost us, okay? So the main trick there was to use the formula intelligently, keeping track of units, yeah? Another example. What is the power output for a 60 kg woman who runs up a 3-meter high flight of stairs in 3.5 seconds, starting from rest, but having a final speed of 2 meters per second? So you read the problem. What's the first thing you do? Yep, you're going to sketch it out. Okay, so approximately, let's say these are the stairs, and here's the person, there's the starting initial position, here's our final position. Her mass is 60 kilograms, okay? And this height here, her entire change in height is 3 meters, okay? And she does it in a time of 3.5 seconds, starting from rest. So we know her initial velocity equals 0. But she has a final velocity here of 2 meters per second. So if we consider these two positions, we can apply conservation of energy here, right? What's the total energy at this point, at this initial point? We can set our potential energy as 0 here, since we are free to set it anywhere as the reference 0. Which means what's our potential energy here? Our final potential energy. It's given by mgh, right? So her mass times gravity times the height gain, which is 3 meters, yeah? What is the kinetic energy here? Well, she starts from 0, so her kinetic energy is 0 at the start. What's her final kinetic energy? Her final kinetic energy is equal to 1/2 mv squared, 1/2 m v final squared, and v final is equal to 2 meters per second. Yeah. So we know all the terms here, and this is her energy output, total energy output, in how much time? In 3.5 seconds. So if we divide this total energy by adding these two, by 3.5 seconds, we should get the power output for this woman. Let's have a look at this. So here's the diagram again. Now you can actually see a person running up, right? Final total energy, sum of kinetic and potential, divided by 3.5. So I've put in the values of 60 kilogram is her mass. V final is 2 meters per second, so square that, mgh here, and that gives you 538.3 joules per second. Yeah? This is a unit of power, so that means 538 watts. Okay. We assume that all we need to consider, we can reduce that person down to 1 point, which is the center of mass of that person, okay? So the change in height of that center of mass is what we used. And so we just wanted to highlight what assumptions we have made in this problem, okay? Now, we saw the work done in a spring case, when you compress the spring with a non-constant force, but when you do have a constant force, let's say here, like this is a red line, it's at a constant level, okay, and it creates a displacement, then also our work done is given by the area, shaded area, which is under the curve. This is my curve, the red one. Between that and the x-axis, positive x direction, between my initial starting position and my final position, this is going to give me the work done. So work done equals F times D, right? Because F is this side of the rectangle, D is this side of the rectangle, and this F is F cosine theta because we remember it was the dot product. Yeah? We already did the one for the spring, half kx squared. Okay, half base into height, we've done all this. Now, you may have a varying force which over this initial position to this final position varies like this, okay? Then also the area under this curve, which is shaded, is going to give you the work done, okay? But it's harder to calculate because the force is not constant here. Okay, let's look at another piece of group work. Suppose that you push a 30 kg package with a constant force of 120 newtons through a distance of 0.8 meters and that the opposing friction force averages 5 newtons. A, calculate the net work done on the package. So if you want to calculate the net work done, the first thing you're going to have to do is to calculate the net force and multiply that with displacement, right? So you know the displacement is 0.8, but what is my net force? I am using a force of 120, there's a friction of 5, so I have 115 times 0.8 should give me part A, yeah? What about part B? Solve the same problem as in part A, this time by finding the work done by each force that contributes to the net force. So you want to find out the work done by 120 kgs, displacement of 0.8, so that's 120 times 0.8. The frictional force, how much is work done to overcome that non-conservative force? It's 5 newtons times 0.8, right? 40 joules. You also have the weight of this. And what work does that do? 0, since the displacement is not in that vertical direction. There's also the normal force. And what work does that do? Also 0. So you just need to write out each of these. And we're going to look at this. There's the 115 net force times the displacement. This is part A, 92 joules. Part B, we're going to break down the work done by each force, and it must equal the same total, 92 joules, right? The work done due to gravity, which is the weight, is 0. Work done due to normal force is 0. Work done by the applied force, which is 120, times 0.8, okay, so that's 96 joules. And work done by the frictional force is negative because it's in the opposite direction to the displacement, so negative 5 times 0.8, so that's going to give me negative 4 joules. I think by mistake I might have said 40 earlier. That's negative 4 joules. I stand corrected, okay? And you can see that all of this sums up to that same total amount of work. Okay, let's read this last problem and then do this, okay? So here we have a picture of a roller coaster going down this and then going to come up here. What is the final speed of the roller coaster? Shown if it starts from rest at the top of a 20-meter hill and work done by frictional forces is negligible. That's part A. Part B, what is its final speed? What is its final speed if its initial speed is 5 meters per second? So let's just consider part A for now. And as soon as you start doing this, in this case, it's already sketched out for you, so you don't need to sketch it, but you do need to decide what. You need to decide where your potential energy is going to be 0. And it seems to me that the height is being measured from here. This is my initial position. This is my final position. I'm not particularly interested in this position since it's not my initial or final. So I can safely set my potential energy equal to 0 at this green line. So this is my reference potential energy. Yeah? And from this reference, initially it's 20 meters high. So I know I'm going to have potential energy here equal to mgh, where h is 20 meters. Yeah? And the mass is the mass of this roller coaster, which we don't really know. But let's just carry on. What is the initial kinetic energy? Kinetic energy is 0 since it starts from rest, and they conveniently gave you that its initial velocity is 0. So the total energy is the sum of these two. And what is the total energy at this final position? At this final position, my potential energy is 0 by definition. We want to find out this velocity. That means it's got a certain velocity, which means it has final kinetic energy equals 1/2 mvf squared. Since there's no initial velocity, I don't need to really write vf. I can just write v mv squared. Yeah. So this is my total final energy. I can set 1/2 mv squared equals mgh. The two m's will cancel out, and I can find the velocity v squared because there are no non-conservative forces. Okay, that's all of part A. Part B, what is the final speed if its initial speed is 5 meters per second? So now in part B, this kinetic energy is no longer 0. It's 1/2 mvi squared, where this is the vi. Yeah? And you need to sum this and set it equal to this. Yeah? Where this is no longer 0. So that's the only difference in part B. Let's look at the solution. And you actually want to sit down and do the solution before you look at it. Okay. So for part A, the initial velocity is 0. We have 1/2 mv squared equals mgh. This gives me a velocity v of almost 20 meters per second, which is 19.8 exactly. Part B, I have some initial kinetic energy, right? Sorry, this is my final energy. I have some initial kinetic energy here. Let's just clear it. This is the initial kinetic energy added on to the potential energy. And we still need to find this velocity, the final velocity. And it comes out to be 20.4 meters per second. So it's more than it was in this case. Does that make sense? Yes, because it starts off with a greater total energy, right? So it makes sense for it to have greater kinetic energy afterwards, since this potential energy is the same in both cases. Okay. Let's look at one more problem. A 60 kg person jumps onto the floor from a height of 3 meters. He lands stiffly with his knee joints compressing by 0.5 centimeters. Calculate the force on the knee joints. So it's assumed that all the force is taken by the knee joint here. Okay. And let's just, whoa. This is my two positions, jumps from here to this final position, right? And this height here is 3 meters. So what's the total energy here? This is mgh, mass, which is 60 kilograms, g 9.8, h is 3 meters, right? It must be equal to whatever his knee joint absorbs, yeah? That's the difference in potential energy. Since we're going to take our potential energy here to be 0. Okay. And it comes to a stop, so his kinetic energy is also 0. So all this mgh must be absorbed by his knee, right? It's going to be force times distance. This is the force on the knee. The distance is 0.5 centimeters. You need to convert it to meters, right? And you can solve for F. Okay, so that's what you need to do. Let's look at the solution. mgh divided by d, yeah? mg H divided by D is going to give you something of the order of 10 to the power of 5 newtons. That's a significant force on his knee. Okay, so you want to be careful when you jump, you're absorbing quite a lot of force into your body. The only known animal that hops as its main source of locomotion is the kangaroo. Okay, it's a marsupial, and it has specially designed hind legs to be able to cushion that landing because it's going to absorb large forces each time. Okay, we stop